is yours.
Thank you for the introduction and welcome to our presentation. I will show you the work we did with my colleagues at the Network System Security Group at KTH in Sweden. So I will briefly introduce the overview of our presentation. So we'll talk a bit about platooning. So what is platooning? What are the benefits? And of course, then we will move to the relevant literature, some challenges that exist, and of course, our investigation into the problem. So what is a platoon? Essentially, a platoon is a convoy of vehicles that interact with each other, sending some messages, in this example, CAM messages, where they are periodically disseminated every, let's say, 100 milliseconds in order to improve road safety, traffic management, and fuel efficiency. You will see that the vehicles are closer together. The green is the leader and the black is the follower in the platoon, while the cyan non-smart vehicles are essentially spaced together. This will lead to the next slide, which is about how which message every vehicle consumes essentially in the platoon. So we have several intra-platoon information flows. The most typical one is the predecessor leader following topology, because the leader can reach every vehicle in the platoon in a single hop. Now, in order to consume these messages and perform the platooning application, the vehicles are using certain controllers. We categorize them into two categories. One is the constant vehicle spacing, and the other is the constant time gateway controllers. And you can see the four that we are using in the table at the end of the screen. You will notice that with R, we actually denote information that the radar can give to the vehicle, while with V, the information that the controller needs through the V2V communication, the vehicle-to-vehicle communication from the predecessors or the leader. Now, platoons move on the road, but how we form them? So there needs to be a leader, and then, of course, someone needs to enter the platoon. Usually, this happens by the tail of the platoon. For example, a vehicle approaches, signifies to the leader that he wants to join, and he will communicate and join into the platoon. Of course, the same applies if we want to do an exit maneuver. Now, there are benefits to actually implementing maneuvers that actually allow all the positions of the platoon to be used. For example, we want to join in the middle of the platoon and not at the tail, because let's say we go to the same destination. This means that the vehicles can then exit together, increasing the road safety. The same applies for the engine capabilities or braking capabilities, so you can group vehicles together in order to improve the safety of the passengers. Now, so far, in the related work, in the literature, we have there are papers about how we authenticate these vehicles between each other, what is the privacy, how we achieve privacy in this kind of scenarios, for example, by using pseudonyms and other schemes. And then, of course, there are attacks, like falsification attacks, for example, if you change the position of the vehicle when you send your CAM message to the next vehicle. Or you perform a jamming attack, for example, by a drone flying above the platoon. And similarly, on the other side, we have misbehavior detection schemes, as example, simple plausibility checks or Kalman filter or other machine learning approaches. Now, the challenge here is twofold. So for the first problem, the attacker can be inside the platoon, which means that he has an inherent knowledge of what the platoon is doing and how the protocols work and how the controller of the platoon works. The other problem is that actually the protocols, the maneuvers create a certain problem. For example, you can have misbehavior detection schemes that require a certain intra-platoon distances to be present. For example, you will see in the first two pictures that when the distances start increasing, the detection mechanism, in this case the Kalman filter, actually detects a benign maneuver, either a join or an exit, as an attack, even though there is no attack. Now, similarly, the protocols themselves can actually be a part of the problem. You will see in the second picture that when a vehicle tries to join in the middle of the platoon, certain protocols actually split the platoon into two platoons. But this creates the problem, as we term it, privilege escalation attack, because the third vehicle in this case will become a new leader without any safety or election mechanism between the vehicles. So let's move on to our adversarial model. So what we consider in our scenarios and in our attacks. So we have an internal attacker. He's going to do some falsification attack, meaning he's going to change some values in the distributed messages. Then we can have external jammers. The jammer can be a drone, again flying above the platoon, perhaps jamming all the communications in the vicinity of the vehicles, or perhaps targeting a specific vehicle in the platoon in order to make it harder to detect it. Now, we expand the adversary model by including a collusion attack, meaning an adversary inside the platoon starts a falsification attack and then colludes with a drone flying above the platoon to perform a jamming attack to a vehicle which is a follower of the targeted vehicle. Now, we also add a rationality angle to our investigation, meaning an attacker would actually want an attack to cause a collision that actually doesn't involve his own vehicle. Of course, the attacker can also have malware infected the vehicle, but then in this case, he doesn't care if the vehicle itself crashes. Now, in order so our attacks range from simple naive falsification, meaning we just change the speed to a static value always, and then we move progressively to more interesting or intelligent attack, for example, gradually changing some of the information, for example, the position or the speed or the acceleration of the vehicle. Now, the most intelligent, let's say in this case, would be a combined attack, in which case we gradually change the position, falsify the position, and then the attacker will also actually change the speed and acceleration in order to make the attack harder to detect. Now, we also, as I said already, we're going to include some targeted jamming and then, of course, the collusion scenario. Now, in our scenarios, we consider attacks on static platoons, meaning a platoon that doesn't change in size. For example, it will always stay with 4 vehicles. And then, of course, we have attacks during a join maneuver. You can see the picture on the bottom, or, for example, in an exit maneuver. And then, as a basic setup, we consider some sensor errors in order to approximate real-world scenarios, because the sensors may be not very accurate. And then, of course, we have a long highway in order to make it easier for us to perform the tests and the maneuvers. So, in order to accomplish all of this and then perform all our scenarios, we actually implemented a simulation framework. We call it Artemis, which builds on top of previous frameworks in the literature, for example, the Sumo mobility simulator. Now, our framework includes several modules like attack scenarios, maneuvers, defensive mechanisms, and of course, mitigation capabilities. And then what it allows us to do is actually combine all of these modules in whatever combination we want in order to test the platooning ecosystem as a whole. And of course, we introduce a machine learning module or a Python integration module in order to integrate machine learning algorithms as a defensive mechanism, either offline as a forensic tool, for example, or online during the simulation, essentially. Moving on to the attacks or the impact of the attacks. On the left side, we can see a combined position attack during a join. On the left side, we have a follower performing the attack, and on the right side, we have a leader performing the attack. Now, you will notice that there are 2 sides in each picture. So the bottom, the upper half is when we have a collision, we actually measure the severity, the collision severity, which is measured on the speed difference between the 2 vehicles colliding. On the bottom half of the figure, we actually show the intra-platoon distance between the vehicles. If the dot is actually different than the shaded box, then we know that the controller is affected by the attack and there is an induced instability. Now, the main takeaway here is that when a leader performs the attack, actually the severity is bigger in most of the cases, at least. Now, on the right side, you will notice, you will see a leader position attack during a no maneuver. Essentially, we don't do any maneuver, we just cruising on the road. And you will see that actually the combined attack, the combined position attack, essentially crashes all the controllers regardless if the controller itself requires position information from its predecessor. Now, the same does not apply, of course, for the gradual position attack, where it only affects the consensus controller, which is the third column, essentially. Moving on to the collusion attack, on the left side, you will see the gradual position attack, and then on the right side, on the top pictures, we will see the collusion attack, which includes the gradual position falsification, and of course, at the same time, a targeted jamming. Now, one may hope that a better attack or a more intelligent attack would give a better result, but actually, what we see from the figure is that, for example, a collusion attack actually doesn't crush the third controller, the consensus controller, while the simpler attack, the gradual position, actually does. And this is because the different controllers respond differently to jamming. So if we jam, it's not necessarily that we are actually going to improve our results. Now, another key insight that we found from our investigation, and you can see it in the bottom 2 pictures, is that if the controller of the joiner is different from the controller that the platoon is using, you can actually induce a platoon collision, even though the platoons of the the controller of the platoon is not actually affected by the attack. And this is because any residual information left on the controller of the joiner just before entering the platoon will actually continue happening during the trip. And this will cause the collision with the members of the platoon. Now, I talked about the rationality angle in our adversary model, so it's not very important to discuss exactly whatever is happening here, but what you need to remember is that a green signifies a very potent attack in the sense that the attacker is not part of the collision. And the red means we still have a collision, but if the attacker is inside the vehicle, then he also has the potential to injure himself. You will notice some L and F values here, which means who is performing the attack. Just to show what we can get from this is actually in the next figure. For example, for the path controller in the upper half of the slide, we can see that actually all the green or most of the green cells in the table actually require a follower perform the attack, meaning a leader is not always the best attacker in this case. And we can notice also that the attacks that actually produce the green values are relatively negative values for the path controller. Now, if we move to the consensus controller, we can notice that the only green values, meaning the attacks that don't cause a collision for the attacker, are actually during a join maneuver. So, for example, an attacker in a platoon using the consensus controller would actually attack during a join. Otherwise, it risks harming himself. Now, moving on to to the controller comparison in order to see which attacks works the best, and then maybe what are the weak links for each controller, we find some expected behavior. For example, for the ploy controller in the first table, you will notice that the position and the speed attacks for both simple and gradual are actually 100% resilient because, of course, ploy doesn't use, for example, position and speed into its control algorithm. Now, you will notice, for example, at the end of the third table, that actually the combined falsification attacks actually crush path employed always, like 100% of our test cases. And we can see also that the combined position attack is actually the most potent attack, with the consensus controller actually being the most resilient. Now, so far, we have talked about, how to make an attack, how to crash the vehicles, and what's the impact on the controllers and the passengers. But now let's move to the side from defending from these attacks. So what we're going to use in our schemes is a hidden Markov models. And as a basic, what we need to remember is that each state of the model only is concerned by only from the previous state. And of course, each state will give some observations, and this is what we capture in our defense mechanism. Now, why do we need these hidden Markov models? So we can focus on problem 2 and problem 3. So essentially, we have some observations. So perhaps a speed decrease or a speed increase, or the gap between the vehicles increasing. And then we need to figure out what's the likelihood of this observation corresponding to a model. For example, a join maneuver or an exit maneuver or no maneuver. And in the third problem, actually, by having these observations, we can recreate the state change, which is the first part of this figure here, in order to see if there is a maneuver. Now, so we have some observations, we gather some observations, which is, in our case, is relative distance and relative speed, and then you need to do something with it. You need to train the model. So we apply certain algorithms, in this case, the Baumwelz algorithm and the Peak algorithm, in order to train the problem, to train the model. Now, in this case, we train 3 models, each for its car, for its speed that it's moving. The 3 models correspond to, of course, the join maneuver, the exit maneuver, and the no maneuver. We make use of the big algorithm, essentially, to stop any underfit or overfit to our results. Otherwise, the defensive mechanism would not be very accurate. And you can see in the first picture a result of this, how this big function works with a negative, with the lowest value being always the better. It doesn't matter if it's positive or negative. Now, moving on to, so we have trained the model, we store these models in the vehicles, and then the vehicles start traveling on the road. So we want to detect an attack. So we gather some information, we gather some observations from the vehicles, and then we categorize the 4 methodologies that we use into 2 categories. So we can do a maneuver recognition, and then based on this, make an attack detection, or we can actually go straight to an attack detection and implicitly detect which maneuver we are doing. The first 2, in the first approach, the 2 solutions actually corresponds to problem 2 or problem 3 from the previous, from the second to previous slide. Now, if we focus on the attack detection only, what we do is we use a heuristic in this case called the Hellinger distance to actually figure out which model is actually close, which pair of the models is actually closer together between the training observations and the trip observation. And the other methodology that we use is the log likelihood ratio, which means we just check which of the two pairs is closer together. And then what we do is we have the repository with the models, we have the observations, and then we do these two steps in order to detect if there is an anomaly. Of course, in this case, each result of these four methodologies is going to use a threshold in order to avoid false positives or false negatives, depending on how you see. And then this threshold, we found it, we detected it empirically, essentially, from our investigation. Now, let's jump straight into our results. So we have specific metrics like precision, recall, accuracy, and F1. And in this case, we will only show the F1 result because it provides a middle ground between, let's say, precision and recall. And we will see that from the four methods that we use, the best one is the log likelihood ratio, which gives an F1 result of around 87%, essentially, with Hellinger approach being the second with 85%. Now, we will notice that forward and Viterbi are not very good at this, and this is mainly very good. But this is mainly because the maneuver detection module actually gives not very accurate result. And this effectively affects also the detection rates for our mechanism. Now, you will notice that I mentioned some windows here. So when we try to gather the information, we actually use some sliding windows in order to only keep this information for the relevant detection or maneuver detection or anomaly detection. So in the forward and the Viterbi approach, we actually use a big windows in the form of 9 seconds. You need to remember that each message is every 100 milliseconds. So these are a lot of messages. And then we use these 9 seconds to detect if a maneuver is happening. Now, when we detect which maneuver is happening, then we use the last second only to detect if there is an attack. Now, for the Hellinger and the log likelihood ratio approach, which is only the attack detection approach, we actually only use a 1 second window. And this actually gives us better results with regardless of despite that the sliding window is smaller. So we have the attacks, we have the impact, then of course we have a defensive mechanism to detect them, but of course this is a time critical application. So we need to figure out the overhead of our solution, right? So in this case, we tested with 3 machines. Of course, the blue one is the most fast one, the most powerful one. But the green one actually corresponds to an OBU, meaning an onboard unit that we find in smart cars now in the last 5 or 6 years. Now you will notice that the Viterbi is of course the slowest to make a detection, or to take a decision, and then forward is the fastest. But then LLR, even though the LLR approach, even though it's a bit slower actually than the forward approach, actually gives us better results in terms of detection capability. And we need to remember that even though we see like almost 180 milliseconds, this is still less than 2 beacons. And of course, our sliding window for this case is 1 second. So even this result is not prohibiting to our solution. Yes. So so we have some attacks. We figure out the impact that they have on our platooning application, and then we presented some defensive mechanism, and then of course how the detection rate of our defensive mechanism, and then the overhead that we have. And we can see from our results that actually our solution is good enough in this case, with at least 87% accuracy to detect an attack. Now, we need to remember that this is a detection. So even though you can detect an attack, it's not necessarily true that you will avoid a crash, because this also relies to what mitigation technique you are using. And then, of course, so it depends on effectively what you're doing after you detect an attack and how fast you detect the attack. So this is part of our future work. And I think this is it for me. I think that was a bit fast, actually, but Yeah, I mean, more time for questions, I suppose. And then if you have any questions, I will gladly take them.
Yeah, thank you very much. We like fast speakers.
I'm trying to slow. I'm trying.
Let's see if there is any question. That means they either not listened or you were too fast. Okay. So now we go to first physical and then online. Any physical question? Please.
Hi, thanks for the talk. It was really great. You're talking right at the end about the misbehavior detection, and then sort of the forward case is 10 milliseconds or so to detect the anomaly.
Can you repeat? Sorry.
Oh, yeah, sure. Sorry. Yeah, you were saying in the detection phase, it takes around sort of 10 milliseconds for the detection to reach a result for like the forward case, for example. That slide. Yeah, so about 10-ish milliseconds
for
on
the
average.
blue case, but
but obviously, in the cars it might be the worst case. But if we consider the vehicles, for example, to be safety critical, is this a considerable wait time, would you think? And how did you evaluate that?
Yes. So this green line actually represents essentially this. So because it's a time critical application, we need to know if it's fast enough, right? Or if we can avoid a collision. Now the green actually represents a vehicle performing this because it's an onboard unit essentially. The CPU is the CPU from an onboard unit of a vehicle. And we can see, for example, if we go always by the best approach, right? So if we go, let's say, with the log likelihood ratio, we can see that it's 180 milliseconds. Now, maybe it depends on the attack, and then of course it depends again on the mitigation. I can show a slide after I respond to the question. But this actually effectively stops a lot of the attack that mitigates a lot of the collisions that we had without So it's fast enough in order to mitigate a lot of the collisions, essentially.
My next part was going to be, this is just a detection, and then obviously you have the decision after that, which is, triggering e-stop, for example.
So if I can show something on the appendix, I had it ready, so that it was a good question. So you can notice, for example, that, so you have these CACC controllers, and they communicate with each other, and they perform some calculations in order to change the acceleration back and forth in order to keep the difference. Now, let's say you have an attack. So what usually happens in the platooning application is that if there is an attack, we are going to degrade the performance from CACC to ACC, meaning there is no communication anymore. We break the platoon, and then we increase our intra-platoon distance, right? But this is the base. Now, you can see on the first slide, actually, that if there is an attack, you can actually mitigate it, right? So you can actually detect the attack fast enough and then perform break the platoon and then increase the intra-platoon distance. On the y-axis, we see the distance between the cars, essentially. You can see when the attack starts, the vertical line, when it's the detection, the vehicles suddenly start increasing the distance, right? Because they detect an attack. Now, if you have, for example, a jamming attack at the same time, you can actually see that this doesn't hold anymore. The vehicle will actually go down and crash. So it really depends on what you want to do after you detect the attack and what the attack actually entails. Because if you do also jamming, it's not necessarily that the detection is going to help you, because maybe the controller is susceptible to jamming regardless if you detect the attack, right? Regardless of the falsification attack. So this, I don't know if I answered the question.
No, you did. Thank you.
Okay, so is there any other question? Attendees? Physical? No? Okay.
Hi, thank you. Interesting talk. So one quick question. What if the majority of the platoon itself is malicious? How would that work if someone joined into malicious?
Yes. So, we consider collusion attacks. So if the majority of the platoon is malicious, then you are in for some ride. Because if we need to consider the following. So we have certain flow topologies, right? So if you receive information from your predecessor and the leader, if both of them are malicious, then you don't know what's correct and what's not, right? You can always depend on your sensors, which is your radar, for example. But then in this case, you cannot have platooning, because if you cannot trust the other guy, then it doesn't work, right? So yes, if you don't have majority, essentially, then you cannot make a decision. That's a problem, yes.
Thank you.
So do we have, I don't know, my question in the back, any online question? No? Okay, so I would say in the interest of time, and then there are some handouts with them. And thank you very much.
Thank you very much. Thank you for listening.